The aqua regia process dates back thousands of years, to the ancient Romans. It was called aqua regia, Latin for royal water, because it was, at the time, the only known solution that would dissolve gold. Traditionally, aqua regia consists of either 3 or 4 parts of hydrochloric acid, and 1 part nitric acid. In recent years, however, dry, safer alternatives to nitric acid have come to light. Whether refining gold using nitric acid, sodium nitrate, or MX3, the procedure is essentially the same, and pretty simple and straightforward. Metal is dissolved into solution. The materials that didn't dissolve, stones, plastic, ceramics, etc., are separated from the solution by either filtering or decanting the solution into another container. Free nitrogen ions that are in solution are neutralized by the addition of urea. A selective precipitant is added to the solution to turn the dissolved gold, and nothing else, back into solid, in the form of particles. The solution is either decanted or filtered to recover the gold mud. The gold mud is then rinsed, dried and melted. There are a variety of different chemicals, and different equipment, that you can use to refine your gold. Which chemicals, and which equipment you choose, will define the potential hazards in the refining procedure. In these instructions, we will try to make clear to you everything you need to know, both in procedure and in potential hazards. No matter which chemicals, or which procedure you choose to employ, there is some minimum safety gear you must use. Eye protection. Rubber gloves. Good ventilation. It is advisable to refine your gold out of doors. The traditional form of aqua regia is a combination of nitric and hydrochloric acid. Nitric acid is very hazardous. When combined with hydrochloric and metal, it produces prodigious amounts of brown, very corrosive, toxic gases, including nitric oxide. These fumes are so corrosive that they will rust even high-grade stainless steel, after less than 1 second of exposure. In these instructions, we will include the nitric acid version of aqua regia, but really, there is no good reason to use nitric acid. It is dangerous, expensive, and difficult to obtain. The dry substitutes, either MX3 or sodium nitrate, are far safer, reasonably priced, and easily obtained. After the metal is dissolved into solution, the gold can then be selectively precipitated out of solution, leaving all the other metals dissolved. There are 2 different precipitants that are traditionally used. For large-scale refining, sulfur dioxide gas is the traditional choice. This is both very corrosive and very toxic. Surprisingly, this is actually a good choice for large-scale refining, because large-scale refiners have the hoods, ventilation, and scrubbers to handle this gas, and because the sulfur dioxide produces heavy gold particles that are easily filtered. For smaller-scale refining, the traditional choice of precipitant is sodium metabisulfite. While not as corrosive or toxic as sulfur dioxide gas, it produces, when added to solution, sulfuric acid and sulfur dioxide gas. If using this precipitant, you should precipitate your gold, out of doors, with a good breeze at your back. Otherwise, you will find yourself coughing, and your eyes, tearing. Since there are good, non-toxic alternatives to sodium metabisulfite, notably, quadratic precipitant and ferrous sulfate, there really is no good reason to use sodium metabisulfite. If refining indoors, a complete, sealed, refining system with a fume scrubber, such as the Shor aqua regia system, is strongly recommended. Even when working with environmentally safe materials, such as MX3 dissolving agent and quadratic precipitant, you must still use hydrochloric acid. The acid fumes need to be contained to prevent corrosion of your tools and your lungs. Therefore, a sealed system with a built-in fume scrubber is quite necessary when refining indoors. If working outdoors, you can use ordinary buckets, beakers or jars. Dissolving your metal using muriatic and nitric acids. For every ounce of metal that you are refining, add 40 ml of nitric acid and 120 ml of muriatic acid. Be very careful. The acids and the fumes are very, very corrosive. Dissolving time at room temperature is usually about 1 to 2 hours. Heating the solution will speed the reaction time significantly, but will also increase the fume production. For every increase of 20 degrees Fahrenheit, or 10 degrees centigrade, the speed of the reaction will double. Sodium nitrate dissolves very slowly at room temperature, requiring an extra few hours. Because of extended dissolving time, you may want to heat your acid to speed the dissolving process. However, please note that heating will significantly increase fume production. And, of course, hot acid is potentially much more hazardous than room temperature acid. Add 1 ounce of MX3 concentrate, and 120 ml of hydrochloric, for every ounce of metal that you are refining. MX3 concentrate should dissolve very rapidly. However, some concentrated formulations of hydrochloric inhibit the dissolving of MX3. No worries. If it doesn't dissolve within a minute or two, just add a small amount of water. This slight dilution of the hydrochloric will encourage the MX3 to dissolve much more quickly, and will not have any deleterious effect upon the dissolution of your metal. At room temperature, your metal will dissolve in about 1 to 2 hours. Heating will significantly reduce dissolving time, but will also significantly increase fume production. After all the metal is dissolved, it is common for some materials, such as stones, ceramics, plastics, etc., to be left behind, undissolved, in either your beaker or your filter funnel. Since those materials would contaminate the gold that you will be retrieving from the solution, you need to extract those materials from the solution before precipitating the gold. This is easily done by either decanting or filtering the solution. Decanting is carefully pouring the solution off the top till the beaker is empty of solution. If you prefer to filter, use a Buchner filter funnel and use 2 coffee filters. After filtering or decanting, the solution should be clear of all solids, including particles. The solution may be very, very dark, and that's fine. However, it should not be even a little cloudy or murky. If you see any cloudiness or murkiness, it means that there are particles floating in solution, and you should filter or decant again. Adding urea. Free nitrogen ions can cause some gold to redissolve after it is precipitated out of solution, resulting in gold losses. No worries, adding urea neutralizes all these ions, ensuring that the gold does not redissolve. Place your beaker in a clean white plastic bucket. Though overflows are not common, the bucket will contain the solution if an overflow occurs. Add urea to your solution. If working with either sodium nitrate or MX3 concentrate, just a pinch of urea is usually all that is needed. With nitric acid, however, the quantity of urea required is usually significantly more, though the amount can vary quite a bit from batch to batch. When working with either sodium nitrate or MX3 concentrate, adding urea usually causes no reaction with the acid. That means you don't need to add any more. However, it may react by fizzing. If it fizzes, it means you should add a little more, till it no longer fizzes. Whether working with sodium nitrate, MX3 concentrate, or nitric acid, when the urea stops fizzing, it means that you are done adding it. If working with nitric acid, it is typical that a lot of urea is required. If adding a lot of urea, add it slowly. Though uncommon, sometimes, if adding quickly, the urea reacts violently with the acid. While that kind of reaction is highly unlikely, adding urea, while your beaker is in a bucket, is a good idea. Better safe than sorry. Precipitating gold. There are several different selective precipitants available. If used correctly, all will precipitate gold with a purity of at least 99.95%. Sodium metabisulfite. Sodium metabisulfite is the most commonly used precipitant. It's inexpensive, and works quickly. On the negative side, it's corrosive, toxic, and generally very unpleasant to use. It precipitates very tiny particles of gold, some nano in size. Consequently, some of those gold particles, about 3.5%, pass through filter paper, and are lost. Ferric sulfate. This is a relatively unknown precipitant, but it has excellent qualities. It has no odor, and it precipitates large, heavy particles of gold. These particles are easily recovered, with no losses, by either filtering or decanting. On the downside, ferric sulfate is expensive, and has a relatively short shelf life. Quadratic precipitant. This is an odorless precipitant. It creates large, heavy gold particles. The solution should be heated to 180 degrees Fahrenheit for 30 to 60 minutes. Whichever precipitant you choose to employ, the quantities required are the same. For every weight of metal that you dissolved, weigh out an equal weight of precipitant. Precipitation using sodium metabisulfite. Do this inside of a bucket. Sodium metabisulfite has a tendency to foam out of its container. So add it slowly, and do not heat the solution. Stay well away from the fumes. Typical precipitation time, at room temperature, is about 30 to 60 minutes. Ferric sulfate. This is an odorless precipitant that can be employed at room temperature. Or the solution can be heated for more rapid precipitation. Quadratic precipitant. This is an odorless precipitant. It creates large, heavy gold particles. The solution should be heated to 180 degrees Fahrenheit for 30 to 60 minutes. Testing for dissolved gold. Before pouring off the waste solution, you will want to make absolutely sure that 100% of your dissolved gold has precipitated out of solution. For this test, you need precious metal detection liquid. You can buy this ready-made, or you can put it together yourself. Basically, it's concentrated HCl, infused and saturated with stannous chloride and very pure tin. If purchasing this ready-made, make sure that the label has an expiration date. And replace the solution when the expiration date has passed. A good ready-made solution will have an effective shelf life of 1 year. Homemade solutions have an effective shelf life of 3 months. This test is simple and very sensitive. It will detect dissolved gold up to 4 parts of gold for every 1 million parts of solution. Particles of gold will not be detected by this test. To perform this test, you will need to take a sample of your solution. Traditionally, a pipette is used for this purpose. However, since you only need 1 or 2 drops of solution, you can use an eyedropper or even a glass or plastic stirring rod. Place a drop or 2 on a clean paper towel, mirror, or, as seen here, a drop plate. Add 1 or 2 drops of precious metal test liquid to the sample you just took. If the sample changes color to purple, brown, or black, some gold remains dissolved in solution. In that case, add a little more precipitant and give the gold some more time to precipitate out of solution. Between each test, clean your pipette with water. The inside of the pipette can be cleaned by squeezing and releasing the bulb a few times, while the tip is immersed in water. When your test causes no change in color, that means that no gold remains dissolved in solution, and it is time to recover the precipitated gold. Decanting or filtering. Once the solution has been tested for dissolved gold, and the test confirms that the solution is free of dissolved gold, it is time to either filter, or decant, to recover the gold particles. It is generally considered simpler and easier to decant the solution, rather than to filter it. To decant the solution simply means to pour the solution off slowly and carefully. If filtering, use a Buchner filter funnel with at least 2 layers of coffee filter paper. Save the waste solution, since it is not uncommon for some particles of gold to pass through the filter paper. Save your waste solution. If working with ferric sulfite or quadratic precipitant, your solution is probably free of gold particles. Still, it's best to save the solution, just in case. If working with sodium metabisulfite, particles of gold will be floating in your waste solution. They are hard to see because the solution is dark, and the particles are very tiny. If we make the solution transparent, we can clearly see the particles. Typically, when working with bisulfite, these particles represent about 3.5% of your gold. These particles are very tiny, so they will take several days to settle. Just be patient, and you can recover this metal. You may have to decant and wait several times before all the metal is recovered. But, if you are patient when working with bisulfite, 100% recovery is quite typical. Rinsing. To obtain high purity gold, rinsing is essential. When you filtered or decanted your solution, you poured off the impurities. However, your gold mud still has some solution clinging to it. And that solution has dissolved impurities in it. If your mud was dried and melted at this point, those impurities would contaminate your gold. So rinsing away those impurities is essential. For the first rinse only, ammonia, not water, must be used. The reason is this. If the first rinse is with water, copper hydroxide can precipitate, coating and contaminating the gold with a white, sticky substance. Add at least enough ammonia to cover your gold mud. The ammonia will rapidly turn blue, as it reacts with a small amount of acid that is still clinging to your gold mud. Decant the ammonia, saving the solution. Fill your beaker with water. Tap water is fine. Give the water a good stir, with a clean plastic, or glass stirring rod. The gold particles will settle within a minute, or 2. If sodium metabisulfite was employed, or the particles are tiny for some other reason, it may take a little longer. Once the particles have settled, decant, or filter the water, and then rinse again, with water. 2 rinses is usually enough, but we'll test to make sure. A small amount of water will cling to your gold mud. We'll take a few drops of that water and test it for impurities. Tilt your beaker. Water will drip off the mud and then puddle in the corner of the beaker. Take a sample from the puddled water and place it on a spot plate, mirror, or paper towel. To test, add a drop of ammonia test liquid. If you see any color change, even the palest shade of blue or purple, rinse again, and then test again. When the ammonia test indicates no color change, it's time to give your mud a final rinse with distilled water. The distilled water will wash away any minerals left behind by your tap water. Add a cup or more of distilled water. Give your gold mud some time to settle. Then filter, or decant your water. You can now dry your gold mud, either by air drying, or heating on a hot plate. Please note, do not put a cold beaker on a hot plate. It will shatter. Melting. So now you have highly refined gold powder, and it looks like, well, it looks like dirt. To restore the beautiful, anisotropic gold color, you will need to melt the powder. Typically, melting is done by torch, so that is the method we will illustrate. Here is what you will need. Melting torch. Use a torch made for this purpose. The common propane torch simply will not provide enough BTUs to do the job. Crucible. You can use a standard clay graphite crucible, a ceramic cup-shaped crucible, or you can use a burner ceramic crucible. Crucible rest. Any refractory material, like a brick or a cinder block for example, will do the job. Flux. Common fluxes that are typically used include borax, boric acid, or a combination of the two. Alcohol. Preparing your crucible. Select either an unused crucible, or one that has only been used to melt refined gold. When using a fresh crucible, you must first flux it, sealing its pores, thus preventing it from absorbing gold. Heat your crucible to red hot. Sprinkle flux on the inside of the crucible. A mixture of 50% borax and 50% boric acid is the most commonly used flux. The flux will melt rapidly, forming a thin glaze and sealing the crucible's pores. Wrap your gold powder in jeweler's tissue paper. If that is not available, you can use a small section of a paper towel. Soak the wrapped gold powder in alcohol, and place it in your crucible. The paper and alcohol will help secure the powder, so that the air currents produced by the torch flame don't blow it away. Both paper and alcohol will burn away, leaving no trace. Melt your metal. When it flows like water, pour it into an ingot mold to make a bar of gold, or pour it into ice water to make shot. If you have any questions regarding melting or any other part of the refining process, please feel free to contact Shor. We will be happy to help you. Remember, the only stupid question is the one you don't ask.